All right. So that top reaction, and I'm gonna give you the names and all that stuff too. So that top reaction is going to be an addition of HX to an alkene, right? Sometimes you'll see it called electrophilic addition. Right, and the X and HX, whenever you see that, it's a halogen. Right, so HCl, HBr, HI, it just depends on what acid you're using. So I'm gonna actually draw that out. I'm gonna cut this too, because it's gonna take some. We need more room. So we're gonna draw out. I'm gonna draw that out because you can see here it's a condensed formula. You see the little subscript too, and that's important for this example because this reaction it follows what we call Carbonicos Rule, but I'm gonna explain all that stuff to you. So don't panic about that. So this is all right. So then that side over there has two ethyl groups attached to it. All right, and on this side, you got a hydrogen and a CH2, CH3. Like, is everybody okay with me drawing that CH2, CH3 in skeletal form?
Yes.
Or say again?
I said yes.
All right. So for this reaction, it's a couple of rules to remember, right? The first thing is the alkene is the nucleophile. Right, so your alkene is a nucleophile. That's the first thing. Second rule, which is, and I'm kind of going through it this way because I don't want to start doing the mechanism and then it's like, oh my gosh, what is that? So the second rule is that it always goes through and I'm trying to put it in terms of stuff you already know. It always goes through a carbocation intermediate. And then the final thing is that X is going to add to the most substituted carbon. Right, that third criteria or the third outcome is kind of tied to the second, right? Because if you make a carbocation, the most stable one is going to be which one?
Third degree.
Yeah, it's going to be a more substituted, right? Remember your trend, tertiary is the best, and then secondary, and then primary, and then methyl. Right, that's the trend for carbocation stability. All right, are we okay so far? All right, so when I take this and react it with HX, not try to do that. For HCl in this case, what if the alkene is the nucleophile? What's the first thing that happens?
The double bond breaks.
Yeah, so the double bond is you're going to use those electrons to attack H, and then at the same time you're going to break the HCl bond. This is the reaction itself is going to be an addition. If you remember that when we talked about the different reaction types, it's an addition reaction. So you attack HCl, and then from that you're going to get an intermediate. I'm going to run out of room. Let me zoom in. You're going to get an intermediate that looks like this. The plus charge is going to be on that side, and then you're going to, that H that you took off from HCl is going to add to that side. Right? And that's, we'll put that in brackets. All right? So this is your carbocation intermediate. And if you'll notice, the carbocation is on the tertiary carbon, right? Because it's more stable there. Yes or no? Anybody not see that?
Yes.
Mm-hmm. So that intermediate, then you also have, let me see if I can get some, I gotta add another page. And I'm gonna just copy this down there. Right, so when you get to that intermediate, of course, the chlorine that left up top is still here with four lone pairs around it. And a negative charge. Right? Because the chlorine up top had 3 lone pairs before it left. Right? Questions about that? So what once you get to the intermediate, then what do you think happens next from here? Right, if I'm trying to get to the product, which looks like this, right, if that's my product, what do you think happens? How do I show that from the intermediate? So this is why we did all that arrow pushing and stuff before we got to these reactions, because that should kind of be starting to be second nature now. Like, which one of those two is going to be the nucleophile? The chlorine or the carbocation?
Chlorine.
Chlorine.
Chlorine, right? So what do nucleophiles do? Everything that we do with these reactions is going to be based on the concepts that we learned already: acids and bases, and nucleophiles and electrophiles. All right. So anytime you want to know which way to push an arrow, think about which one is the nucleophile, which one is the electrophile. So the chlorine is the nucleophile. That means the chlorine is going to do the attacking, right? So the chlorine is going to attack the carbocation, like so. And that's how we get to the product. Right, so the chlorine is going to attack that carbocation. It follows, but this reaction follows what we call Carbonicos Rule. Let me write that down for you. Right, it follows Carbonicos Rule. All that means, all it says, is that the halogen is going to add to the most substituted carbon. That's it. Right. So, and we just saw that. So for this type of addition, the halogen adds to the most substituted carbon. What do I mean by most substituted?
Doesn't that mean like the most stable?
Okay, that's true.
Like it was the tertiary.
Yes. Yes.
It's like
Dr. Russell.
Yes.
I'm sorry. I'm so sorry to interrupt, but there's somebody that has their mic on and they're making like loud noise in the background. I can't really hear you.
All right. I think everybody's muted now. All right.
Thank you.
Mm-hmm. So let me go back and tell you something about this pen. I'm gonna slap whoever invented it. All right, so the most substituted carbon is where your halogen is going to add. So when we start, the way to think about that is, if you remember when we did alkenes and we talked about disubstituted, monosubstituted, when we did the elimination reactions, and we talked about how alkenes can be monosubstituted, disubstituted. If you look at your alkene from the very beginning for this reaction, the carbon that's more substituted is going to be the carbon where your halogen ends up. Even if you don't know the mechanism, you can still predict the products. All right, so look for that. Like the alkene itself in this particular instance is tri-substituted, right? But the carbon on the left, this side, has more carbons attached to it than the carbon on the right. So this is your most substituted side right here. Right, that's your most substituted side. All right. So that's the mechanism and the outcome, the product for a electrophilic addition of HX. Right. Sometimes you'll hear it called addition of HX or electrophilic addition of HX. And then the outcome of that reaction, because all these reactions give you new functional groups, right? You started with an alkene, ended up with an alkyl halide. Right? You ended up with an alkyl halide. The alkyl halide is exactly what the name sounds like, right? If you notice, it's all carbon, hydrogen single bonds, and then it has a halogen somewhere in that structure. So that alkyl halide functional group is the result of, that's how one way to make alkyl halides is to take alkenes and add HX to them. All right. Any questions so far? So on a flashcard, this is the title of the reaction, electrophilic addition of HX. And then you can just draw in, you can use this reaction on a flashcard if you choose to. But you would draw in your alkene plus HCl, HBr, HI, doesn't matter. All right. There's a two other reactions that we're going to do, and then we're going to stop. Any questions about that?
No, sir.
All right. Let's look at the halogenation reactions, because this is another reaction that we're going to go through the mechanism for that, as well as the products, as well as some other kind of useful information about it. And when I give all these little like tips and things like that I'm giving you about the reaction, that's the kind of stuff on the back side of your flashcard, right? That you can have on the back side of your flashcard, right? Stereochemistry type stuff, regiochemistry. That's what we used to talk about. Carbonicos Rule. That's a regiochemistry term. Regiochemistry just means. Let me go back up to here. It tells you what region the halogen is adding to. Right, so if you got a competition, kind of like a competition between the two carbons in the alkene, one of those carbons is going to get the halogen added to it, the other gets the hydrogen. So that's what you call regiochemistry. Right, there's a region where the halogen goes, and then there's a region where the hydrogen goes. So that's what Carbonicos Rule is dealing with. All right, so let's look at this, the next reaction, which is a halogenation. Right, and that is, it's another addition reaction. Right, addition of a halogen, X2. X again is kind of a generic descriptor for halogen. All right, and if you add a halogen to an alkene, there's a couple of things you have to remember about that, and that is one, that it always does what we call trans addition. And then the second thing is that it goes through what we call a Halogenation intermediate. And I'm going to explain all that. All right, so every halogen addition to an alkene, right? Because keep in mind that's the umbrella we're working under. We're only dealing with alkenes, right? So let me paste this in here, and then we're gonna look at the outcome. All right, so I'm gonna draw the product first, and then we're gonna go back and we'll see how it happens. Is that okay?
Yes, sir.
Even though I hate drawing 7-member rings, we can do it. I'm an OG with the rings. Not so much with this stylus though. I hate it. All right, so you can see the double bond was right here. So once you react that double bond with the halogen, right, you got two chlorines, because the halogens are all diatomic, right? So you got two chlorines. So what happens is we're going to get one here, and then one here, right? The reason they look like that is because of the mechanism, because of the intermediate. And I'm gonna show you that. So one halogen here and one here. Notice the one on the dash line, what that means is that it's going back into the page. And then the one on the wedge is coming out of the page. So this is what you call trans stereochemistry. Right? All that means is that the two groups are opposite to one another. Just like on a trans double bond, right? You had the double bond with the two groups attached on opposite sides. Here, trans means the same thing. The two chlorines are opposite to one another. Sometimes you'll also see it written as anti-stereochemistry. All right. Any questions about that? So what's the term stereochemistry? It's just a way to talk about like the 3D orientation of the atoms, right? So the
Dr. Russell,
yes,
I have a question.
go ahead.
When I'm looking at it, like just looking at it, it looks like cis to me.
Yeah,
So
I was
can you
just about
explain a
to
little
ask
bit?
that.
Yeah, can you explain a little bit like why it's trans exactly?
Okay, so let me do it this way. So if you drew it flat like this, right, one chlorine would be pointed down like that, and the other one will be pointed up like that. You follow me? So the one on the one on the wedge will be pointed up, and the one on the dash will be pointed back.
Okay, so like you said, one was going in, one was coming out.
Yeah,
Okay.
because the dash line means it's going back into the page, away from you, and the wedge line means that it's coming out at you.
So if it didn't have a dash line and it just had like the wedge line for the other CL, would it be cis?
Yes, if
Okay.
both groups were wedged or both were dashed, yes, it would be cis.
All right. Thank you.
Good question. All right. So stereochemistry is dealing with the 3D orientation of an atom or of a particular carbon, right? So let's see how we got to that point. All right, so let's go through that mechanism. And remember, all of these mechanisms, the alkene is the nucleophile. Right. So the first arrow that you draw in any of these mechanisms is going to be from the alkene to something. Right. So let me. So that's my 7-member ring. Yes, it's ugly. It's Halloween though. It can be ugly. And that's plus chlorine, right? So the first thing that happens is this is going to attack chlorine and break that chlorine sigma bond. Right? This is nothing new. You've seen all this stuff before because it's a basic nucleophile. So alkene is my nucleophile. And then the chlorine is my electrophile. All right. Now I'm going to show you this because sometimes it gets glossed over when we're talking about the halogenation mechanism. But so I'm gonna show two intermediates, right? Because I don't want you to miss it, and I'll explain why I'm showing it like that in a minute. Because normally, if you see it in the book, it won't show you the precursor to the intermediate. It'll just show you the intermediate. So I'm gonna show you both. So here, hold up. So here, I'm gonna put the chlorine here and a plus charge here, right? Because when I break that carbon-carbon pi bond to attack chlorine, the other carbon in that pi bond is gonna become positive when I break that bond. Are y'all following that? Because I took electrons away from it. Anybody not catching that? All right. But this doesn't stay like this. It actually collapses and closes. Boom. So that's gonna attack the carbon, carbocation, and then you're gonna end up with a intermediate that looks like this. And I'm gonna draw it way edged. And now the chlorine is positive. So you have a carbocation, but the chlorine collapses on it. And if it's internal like that, when the chlorine attacks that carbocation, we say that it's intramolecular.
Dr. Russell, why is it internal?
Well, it's so the chlorine is electron rich and is next door to a carbocation, and so it just happens, right? It just closes, right? Keep in mind, you still have this chlorine out here that you lost when you broke the chlorine sigma bond, right? But that intramolecular attack is faster than the other chlorine attacking. So it just closes up really quickly. Just basically due to proximity. You understand what I'm saying? Like that chlorine with those long pairs is just sitting right next to that carbocation. So it's going to attack it.
Okay.
Does it make sense? Does that make sense?
To a degree.
Okay. Well, it's better. A degree is good right now. We'll take that. All right.
Excuse me, I have a quick question before you move on.
Go ahead.
Why'd you say that there was a positive charge on that hydrogen again right there?
On the carbon?
Yeah, the carbon. Sorry.
Because I use those electrons in the pi bond over here.
It's because you donated that pi bond to the chlorine, right?
Yeah. And you notice only one of the two carbons in the pi bond picked up an atom. The other one didn't. So I took electrons away from it so that the top carbon could pick up chlorine. And in doing that, I made it positive. Anytime you take electrons away from an atom, it's going to become positive.
Okay, thank you.
Good question. All right, everybody okay so far? All right, so notice so this right here, that's what we call in this case, it's a chlorinium, but normally we'll call it a halonium if it's just a generic halogen, right? So that is that's the main intermediate for halogenation. That little 3-membered chlorinium ion or bromonium if it's bromine, or iodonium if it's iodine. That little intermediate is common to all your halogenation reactions. And it's the reason why the stereochemistry is trans, right? So think about it. If this is on a wedge, let me see if I can. Right, if this is wedged coming up out of the page, right? The other chlorine, when it comes in to attack, it's not going to attack from the same side where that chlorine is. So it's got to come from the opposite side. So when this comes in to attack here, right? Oh, that's a bad arrow, sorry. When it comes into attack, it's going to attack from the opposite side. That's why you get that stereochemistry. Right, so if I were to draw it out flat, that chlorine is up here. Right, of course, all the rest of the rings are all back here. Right, so the other chlorine, when it comes in, it's not going to come from here, because that's going to cause problems. Right, it's not going to come from here. Right, because first of all, chlorine is big. It's got a big atomic radius. So it's taking up a lot of space up on the top side. And then if the other chlorine tried to come in, it would incur what we call steric interference, right? That just means that the groups are big enough to touch. And when they do, it's going to make the energy go up. So the other chlorine that attacks the intermediate has got to come from the opposite side. Right? It costs too much energy for that chlorine to come from the same face, right? And you don't want that steric interference like that. That's bad. It's going to jack the energy of the reaction up, and anytime you increase the energy necessary for a reaction to happen, the reaction is not going to happen, or it's going to slow way down. All right, questions? Any questions about that?
I got a question.
Go
So
ahead.
when you say the opposite side,
Mm-hmm.
and you drew it right there, do you mean the opposite side from what? Because when the chlorine first attached, it was on the left side, and then
No, no,
that's
no.
what you mean?
Let me
You
not
mean like
say
top and
opposite
bottom?
side. Let me say opposite face.
Okay.
You following? Let me give you an example of what I'm talking about. So with an alkene, if I have a generic alkene like this, right? I got a top face and I got a bottom face. Right. So with that intermediate, you're gonna have the same kind of concept going, right? You have a top face and you have a bottom face. So the chlorine, the other chlorine, when it comes in, is going to attack the opposite face. Because I think I know what you're saying. You're saying up here, it can attack either this side or that side. Is that what you're getting at?
Yeah, that's what I was asking.
Yeah, yeah. No, it's the face and not the side. I should have said that differently.
Okay, and then when you draw it, you have to draw those dashed lines since it's opposite.
Yeah, and so that's why you see in the product a dash and a wet. So here with the other chlorine, I should have drawn that the opposite. Let me change that because I wanted to be accurate based on the mechanism. All right. Any other questions about that? Y'all some troopers, man. It's 8:42. My other class, we met at 7 and only I think 3 people showed up. I do get it though. It is kind of a big ask to move a class from 9:30 in the morning and 7 at night. But it's not like it ain't every day. All right, so what do we know about this reaction? Right? The addition is always trans, and it goes through this 3-membered Halogenation intermediate, right? And that is, so the intermediate is the reason why you get the trans addition, right? Because the intermediate is going to form in such a way where the two halogens have to be on opposite faces. All right. Any other questions about anything? I think I'm gonna wait and do that halohydrin formation. This one right here. I think it was in the last video though, but I'm gonna wait and do it because I don't want to overwhelm you because it's late. Anybody feeling overwhelmed? You can tell the truth. It's only a few of us here.
Yes.
You
For
said
sure.
yeah.
Mhm. Tired.
So what is it? What's the most overwhelming part? Is it remembering the nucleophile electrophile stuff, or is it just what? You got to help me.
Remembering all of the components that go with which, you know.
Yeah.
So that's why you need to make some flashcards.
Right.
That's the purpose of the flashcards. Because once you see the reagents, the outcome becomes second nature. You understand what I'm saying? Oh, I got an alkene. I'm reacting it with chlorine or bromine or I2 or Br2 or Cl2. Oh, this is a halogenation. Once you see that, that's second. The mechanism part, I get. I can understand how that can be overwhelming because it's a lot of arrows and you got all these intermediates and all this stuff. But actually knowing the outcome of the reaction, if you make those flashcards like I told you and you study them, I promise you, it wouldn't. Knowing what happens is not going to be the problem. Knowing how it happens, sometimes I get it. You know, those mechanisms can be pretty intense, especially for the next set of reactions we're doing with the hydroboration, and oxymercuration. Those are very intense, long drawn out mechanisms. But the outcome is also very important too, knowing what you get, you know. So that's why I stress making them flashcards, and then on the backside, if you want to put the mechanism, do that. If you want, but you definitely should put the characteristics of the reaction on the backside, whether it's more Carbonikov, whether it's trans or cis or any of that. All that stuff needs to be on the back. This is the hardest part of the class. I'm just be honest, because it's a lot of information in a really short period of time.